So in this video, we're going to talk about another application of max flow and min cut, but this one is going to be on a specific example, more of like a word problem. So here we're given two companies, Pineapple and Nanosoft, because I guess Apple and Microsoft are not cool anymore. And they're each creating M different software products, and both companies make different versions. So in particular, we're assuming for each product I that Pineapple charges PI and Nanosoft charges NI for that same product. And your goal is to buy one of each products. And each time you buy a product, you pay PI or NI. But also, lots of companies want you to stick with a single company. They don't want you switching between different companies. So you're also given this cost CIJ, which is what you additionally have to pay if you buy certain products from Pineapple and certain ones from Microsoft or Nanosoft. So you could think of it like you buy some MacBook and then you buy a Surface Pro. Well, then since you bought two things of a different, you bought a tablet from one place but a laptop from the other, so you get the equivalent compatibility cost for laptop and tablet. Overall, you want to buy one product from one product of each type, and your goal is to minimize this total cost. So overall, you want to pick two sets, P and N, where P is some set of Pineapple products, N is some set of Nanosoft products, and the union of both is all M products. So for each product I, you're going to decide, am I going to buy the Pineapple version or am I going to buy the Nanosoft version? And then once you've picked your sets, you can look at the cost function, which is going to be the sum of all the items you bought from Pineapple of their price, plus the sum of all the items you bought from Nanosoft of their price. And then for each pair of products, you also have to pay the compatibility cost. And your goal is to pick these products and make these decisions to minimize your total cost. So naturally, we see minimize cost. You might think min cut, which would be a generally good rule of thumb. And so we need to construct some kind of graph to where the min cut in this graph corresponds to the cost. Somehow we need prices to appear as capacities on the edges. So we're going to do something like max matching. So we'll have a node S. We'll have all the Pineapple products. Well, actually, we'll just have all the products. So here we have a single list of all the products. So let me just, this giant list here. All M products. And you'll have a single sync T. And the idea here is when we take a cut, we want prices to appear somewhere. So basically, we'll have the S edges deal with prices from Pineapple. So for each product, product 1, product 2, all the way down to product M, this edge will be the price Pineapple has for item 1, and so on. So when we take a cut, we're taking into account the prices of those versions of the product. And then similarly, we will have Nanosoft's prices will appear in the cut as edges to T. So if we picked a cut right now, let's say this cut, then in total, we're taking into account the prices to buy item 1 and item 2 from Pineapple and the prices to buy everything else from Nanosoft. So the capacity of the cut is roughly giving us what we want, but it's not taking into account the incompatibility part. So how do we deal with incompatibility? Well, we're just going to add some extra edges between nodes. So we'll have in both directions, and this will be C of 1, 2, C of 1, 2. So the reason it's going in both directions is because technically this is an undirected function. The incompatibility if you buy item I first and then j is the same as if you bought item j first and then I. In general, but for this problem, let's make it simple and just assume it's directed. So this one is always the pineapple product and this one is always the nanosoft product. So then we'll have just directed edges. So we'll have 1 to 2. This is C 1 to 2. And this one's C of 2 to 1. And so on. So this is a more general version where you could have different compatibility costs in different directions. Let's actually keep it symmetric. We'll just have it be C of 1, 2 for both. Similarly, you have C of 2m, C of 2m, and so on. So this is going to become a really complicated graph with a lot of edges in the middle. Between every single pair of products, we'll have an edge of Cij, and similarly an edge backwards of Cij. So that's going to be our graph G that we create for our reduction. And then once we have this graph, all we're going to do is our algorithm is going to be construct G and solve min-cut. So in particular, we're going to have the capacity of edge S2I is Pi. The capacity of the edge I to T is Ni. And the capacity of the edge I to J is going to be Cij. So those are our capacities in our graph, and there's equivalent edges for each capacity listed. Then, of course, our vertices, these are just S, T, and then all the products. All M products. So that's our graph G, formally. So make sure you're always specifying what your graph is. That is not a rectangle. So that's our graph. We can build it in linear time. Well, actually, we can build it in quadratic time in terms of the number of items, but it's going to be linear time in terms of everything. But either way, it's going to be very efficient. So we construct G and solve the min-cut. And now if we just want to know the total price, that's all we have to do. So we return the capacity of ST if just want the cost. But if we want to know the products, we put item I in P if S2I crosses the cut, and we put I in N if I to T crosses the cut. In other words, we put I in P exactly when I was in T. So equivalently, this is I was in T, and this would be when I is in S. Okay, so that's our algorithm. How long is it going to take? Well, to construct the graph, it's going to take something like O of m or O of m squared. So let's just look at the worst case scenario and say it's O of m squared just to brute force make all the edges. So this is to build G. Now max flow min cut, if we're going to use min cut, that's going to take O of V times E, which is equal to O of M. So we have M total vertices, and then we'll have M squared edges, so that's going to be M cubed time to run Orland's algorithm. Now it's important here we're using Orland's algorithm and not, say, Ford-Fulkerson, because these capacities might be very large, and so the value of the max cut or the max flow might be super large. And when that's the case, Ford-Fulkerson is slow. So overall, we add these and get O of m cubed total time. Depending on how Cij is represented. But otherwise, it's pretty fast. So that's the algorithm. Now we need to argue that the reduction's correct, so we need to prove a lemma that there exists, or the minimum, we need the minimum possible cost of P and N. We want that to equal the minimum cut. So we want the min cost P of N. We want that to equal to the min cut ST in G. So the proof of this is going to be pretty straightforward because we're constructing it to do this. So basically, if you were given a specific choice of P and N, you could create an equivalent set. So for the first case, given P and N, so this is going to prove that the min cut is smaller than, so it'll be this direction. So given P and N, we create a cut where we let S equal S union all the items in N. So let me just say it's S union N. And T is going to be little t union all the things in P. So remember, this is what we're doing anyway. That's what this is doing. We're basically putting all the items in T into P and removing the little t and taking everything in N if it was in S. So this is almost directly what the algorithm's doing anyway. Now what's the capacity of this cut? We want to show it's at least the cost. So notice that just based on the edges we have, everything that has an edge from S to something in T will have cost P. So this is going to be the sum of all things in T. So I'll say I in T of the capacity of the edge I to little t. So that's from, so anything in T. Oh, sorry, if it's in T, then it's from S. So if it's in T, then the edges are of the form S to I. Otherwise, we have everything in S. And I guess to be very specific, we're not going to consider little t. We don't consider little s. But, you know, that's obvious because any edge from S or T would be 0 because it's not defined. So this is I to little t. And then we also have The last case is I is in S and J is in T of the capacity of I to J. So those are all the types of edges that will leave S and enter, leave some specific cut S and enter T. So either the edges go from little s directly to an item I, they go from something in S and cross to little t, a product to T, or they go like this from a product to another product. Or specifically it'd be this direction, so it'd go from M to 2. So those are all possible edges, and so we get those specific capacities. So now if we just rewrite this, well, by definition, these are the P's. So this is the sum of all Pi, where I is in T, but not little t, plus the sum of all Ni, where I is in S, but not little s, and then plus the sum of all I in S, J and T of Cij. So now by definition, remember, S without S is just all of N, and T without T is just all of P. So we can really just call this P, and we can call this N. And so similarly, this is just going to be N, and this is going to be P. But they're symmetric, so it doesn't matter. Okay? So this is exactly, by definition, the cost of the Pn partition. And so if we pick any cut, this actually works for both directions at the same time. So if we have any cut, we can create this partition, and it'll have the same cost. And we can do the opposite at the same time. So if we have any cut, and we do that trick of just making P equal to T minus T and N equal to S minus S, then literally we just reverse the steps. Because it's an exact equality. So either way, if we have a specific cut, we can construct P and N, and we see that its value will be the same as the capacity of the cut. Or given P and N, we can create a cut, and we see that it has equal capacity. So either way, we get the exact same cost. And so this proves, in particular, the minimum cost solution is equal to the minimum capacity cut in G. And so the algorithm is correct.